Today's artificial intelligence models can pass the bar exam, generate photorealistic images, and write functioning code in seconds. But take them 1 millimeter outside their training data, and they break. With top-down neural networks, engineers manually define the architecture, snapping rigid pathways into place. The grid flows perfectly green for its exact programmed task, but introduce one unanticipated anomaly, and the structure shatters entirely, blind to anything outside its narrow parameters. We constrain these networks by forcing them to mirror our own logic. They exist inside the bias bubble of human imagination, limited strictly to what a programmer can actively predict. Train a robotics algorithm to navigate a perfectly flat laboratory floor, and it glides effortlessly. Place that exact same robot on a gravel driveway, and it freezes, entirely incapable of adapting to a textured surface. If we want to create a system capable of solving problems we can't comprehend, we have to stop dictating how it thinks. True general intelligence requires letting go of the steering wheel. We have to discard the blueprint and figure out how to let the networks grow on their own. Engineers are beginning to test a completely different approach. The emerging field of developmental robotics explores what happens when we let an artificial brain undergo algorithmic growth. Instead of hard-coding rules, researchers start with an empty slate. The system receives a single goal and learns purely through trial and error, a process known as reinforcement learning. Take a look at this digital space. This represents how systems like DeepMind's AlphaZero and MuZero learn. Without a single human rule, they teach themselves by colliding and organizing through millions of iterations of self-play. MuZero doesn't even need to be told the rules of a game. It deduces them from scratch. The complexity of the network unfolds organically. Through minimal initial input, the system continuously adjusts its own internal weights and connections, expanding as it acquires new information. Because the machine isn't restricted by human logic, it frequently arrives at highly robust, deeply non-intuitive solutions that human engineers would never have conceived. This process of unfolding information closely mirrors the architecture of biological brains, driving a methodology researchers call computational evolution. This diagram illustrates computational evolution in action. Rather than coding a static network, programmers use a simulated genome. This glowing seed node dynamically grows, prunes, and rewires its connections based on constant environmental feedback. When forced to undergo this developmental process over time, it stabilizes into multiple distinct topological clusters highly resilient to disruption. When researchers analyze these machine-generated architectures, they find that they map exactly onto structures that naturally evolved in biological organisms. By forcing an algorithm to grow rather than just compute, the network sheds its brittle nature. It begins to behave and adapt like a living, resilient organism. If we accept that intelligence should grow like an organism, we have to ask where the instructions for that growth actually begin. We are looking for the root of what researchers call the fundamental information question. That origin point reaches back billions of years, to the sun shooting photons at a lifeless rock in space. Over eons, that continuous energy powers a specific algorithmic process. It drives the evolution of things, life, brains, and eventually the engineers who build artificial brains. Evolution stores energy as information, building ordered intelligence locally. This requires increasing disorder elsewhere, information entropy. Building AI continues this chain. Letting systems grow from scratch accelerates the very algorithmic process the sun started on that rock. Intelligence, then, is the universe's ancient mechanism for organizing energy to resist the pull of chaos. Understanding intelligence on this cosmic scale carries a warning, one captured perfectly in Douglas Adams' science fiction story of Trin-Tragula and the Total Perspective Vortex. Trin-Tragula was a scientist who built a machine to plug a human brain directly into the entirety of reality. He wanted to force a single mind to instantly comprehend the whole infinity of creation and its exact place within it. The shock completely annihilated the brain. Tragula concluded that for life to exist in a universe of this size, the one thing it cannot afford to have is a sense of proportion. It needs a filter. Top-down engineering is our total perspective vortex. When we try to manually program an AI to handle the infinite possibilities of the real world all at once, the system is overwhelmed. It becomes rigid, brittle, and doomed to fail. To survive in a universe of infinite entropy, true general intelligence cannot be assembled in a single stroke. It must be planted as a seed, given boundaries, and left to organically outgrow its creators.